At the end of this video, you should be able to describe how force affects the motion of an object and interpret and construct free body diagrams.
To move a piano, one of these students is pushing it and the other is pulling it. Each student is exerting a force on the piano. A force has both magnitude and direction. It is measured in units of newtons. The student on the left is exerting a force of 25 newtons to the right. The student on the right is exerting a force of 20 newtons also to the right. Together, the students are exerting a net force on the piano. This net force is an unbalanced force on the piano and causes the piano to move to the right. An unbalanced force is always necessary to move an object from rest. An unbalanced force is also necessary to change the motion of an object that is already moving. Balanced forces cause no change in the motion of an object, whether it is moving or at rest.
Chapter 4, Section 1, Changes in Motion. Force. You exert a force on a ball when you throw or kick the ball, and you exert a force on a chair when you sit in the chair. Forces describe the interactions between an object and its environment. Forces can cause accelerations. In many situations, a force exerted on an object can change the object's velocity with respect to time. Some examples of these situations are shown in Figure 1.1 on the screen now. A force can cause a stationary object to move, as when you throw a ball. Force can also cause moving objects to stop, as when you catch a ball. A force can also cause a moving object to change direction, such as when a baseball collides with a bat and flies off in another direction. Notice that in each of these cases, the force is responsible for a change in velocity with respect to time, aka an acceleration. The SI unit of force is the Newton. The SI unit of force is the Newton, named after Sir Isaac Newton, who lived from 1642 to 1727, and whose work contributed much to the modern understanding of force and motion. The Newton, represented by capital N, is defined as the amount of force that, when acting on a 1 kilogram mass, produces an acceleration of 1 meter per second squared. Therefore, 1 Newton is equal to 1 kilogram times 1 meter per second squared. The weight of an object is a measure of the magnitude of the gravitational force exerted on the object. It is a result of the interaction of an object's mass with the gravitational field of another object, such as Earth. As is shown in Figure 1.2 on the screen now, many of the terms and units you use every day to talk about weight are really units of force that can be converted to newtons. For example, a 1/4 pound stick of margarine has a weight equivalent to a force of about 1 newton, as is represented by the following conversions. 1 pound is equal to 4.448 newtons, and 1 newton is equal to 0.225 pounds. Forces can act through contact or at a distance. If you pull on a spring, the spring stretches. If you pull on a wagon, the wagon moves. When a football is caught, its motion is stopped. These pushes and pulls are examples of contact forces, which are so named because they result from physical contact between two objects. Contact forces are usually easy to identify when you analyze the situation. Another class of forces, called field forces, do not involve physical contact between two objects. One example of this kind of force is gravitational force. Whenever an object falls to Earth, the object is accelerated by Earth's gravity. In other words, Earth exerts a force on the object even when Earth is not in immediate physical contact with the object. Another common example of a field force is the attraction or repulsion between electric charges. You can observe this force by rubbing a balloon against your hair and then observing how little pieces of paper appear to jump up and cling to the balloon surface, as is shown in Figure 1.3 on the screen now. The paper is pulled up by the balloon's electric field. This type of field force is discussed in detail in the chapter electric forces and fields. The theory of fields was developed as a tool to explain how objects could exert force on each other without touching. According to this theory, masses create gravitational fields in the space around them. An object falls to Earth because of the interaction between the object's mass and the Earth's gravitational field. Similarly, charged objects create electromagnetic fields. The distinction between contact fields and field forces is useful when dealing with forces that we observe at the macroscopic level. Macroscopic refers to the realm of phenomena that are visible to the naked eye. As we will see later, all macroscopic contact forces are usually due to microscopic field forces. For instance, contact forces in a collision are due to electric fields between atoms and molecules. In fact, every force can be categorized as one of 4 fundamental field forces.
Contact forces can arise only from the physical contact of 2 objects. Other forces, called field forces, do not require physical contact between objects. One example of this kind of force is gravity. The Earth exerts a force on the ball, even when they are not in immediate physical contact. Consider the baseball again. Other than the bat, what else does the ball come in contact with? The air. As the ball moves, it comes in contact with molecules in the air and experiences friction. All forms of friction are contact forces.
Force diagrams. When you push a toy car, it accelerates. If you push the car harder, the acceleration will be greater. In other words, the acceleration of the car depends on the force's magnitude. The direction in which the car moves depends on the direction of the force. For example, if you push the toy car from the front, the car will move in a different direction than if you push it from behind. Force is a vector. Because the effect of a force depends on both magnitude and direction, force is a vector quantity. Diagrams that show force vectors as arrows, such as the one on the screen here, are called force diagrams. In this book, the arrows used to represent forces are blue. The tail of an arrow is attached to the object on which the force is acting. The force vector points in the direction of the force, and its length is proportional to the magnitude of the force. In this chapter, we will disregard the size and shape of objects and assume that all forces act at the center of an object. Therefore, all forces are drawn as if they act at that point, no matter where the force is applied. A free body diagram helps analyze the situation. After engineers analyzing a test car crash have identified all of the forces involved, they isolate the car from the other objects in its environment. One of their goals is to determine which forces affect the car and its passengers. Figure B on the screen here is a free body diagram. This diagram represents the same collision that the force diagram A, also on the screen, does, but shows only the car and the forces acting on the car. The forces exerted by the car on other objects are not included in the free body diagram because they do not affect the motion of the car. A free body diagram is used to analyze only the forces affecting the motion of a single object. Free body diagrams are constructed and analyzed just like other vector diagrams. In sample problem A in this section, you will learn to draw free body diagrams and some situations described in this course. Later, you will learn to use free body diagrams to find component and resultant forces.
A force is a push or a pull exerted on an object. Consider the situation shown here. To completely understand the motion of the toy, we will identify each force that acts on it. We begin by drawing a free body diagram. A free body diagram isolates the object in question and identifies each force that acts on that object. Let's draw a rectangle to represent the toy. We don't need to draw any of the items that touch or act on the body, such as the ramp or the rope. Next, we identify and label each of the forces that act on the toy. First, consider gravity. The direction of this force is always straight down. We will label it F sub G. Now let's consider the contact force between the toy and the ramp. Contact forces always act in a direction perpendicular to the surface of contact. The word normal means perpendicular. Physicists refer to contact forces as normal forces in order to remind them of the direction that the forces act. Next, we think about the rope. Ropes cannot push, they can only pull along their length. The direction of the force on our free body diagram will be drawn accordingly. The final force we must consider is the force of friction. Friction always acts in the direction opposite the motion or potential motion. In this case, the toy is being pulled uphill. The motion is up the ramp, so the friction force is down the ramp. If we let go of the rope, the toy will slide downhill. Friction now points uphill. The final step is to add up all the forces. For this situation, the best choice would be to break each force into its components parallel and normal to the ramp. You can then find the net force on the object and therefore the change in motion in both directions.
At this point, you should be able to describe how force affects the motion of an object and interpret and construct free body diagrams.